All right, trick question, right? State how it varies, right? And the answer is that it doesn't vary. It's kind of like asking some poor kid, which of these pigs is your parent? When none of the pigs are their parent, right? Their parents. Shout out to Spirited Away, baby. All right. And the reason that it doesn't is, well, we can just show that, right? If the radius of a nucleus is the Fermi radius, a to the 1/3, right? Of course, that by the way, this is predicated on there being a constant nuclear density, right? Um, then our density would be mass divided by volume, right? And that mass is going to be the atomic mass number, and every nucleon is about 1.661 times 10 to the minus 27th, and that's kilograms per atomic mass unit, right? Okay. Let me make sure I'm giving you the right number here. This is from your data packet. Indeed, I did give the right number there. Okay. And then our volume is 4/3 pi r to the third, right? Well, r is just r naught, a to the 1/3, right? And then that's to the third. So notice that we've got an a in the numerator and an a in the denominator, and it just goes away, right? A to the 1/3 to the third is just a, right? And so you end up with the nuclear mass or nuclear density being 1.661 times 10 to the minus 27th divided by 4/3 pi times the Fermi radius 1.2 times 10 to the minus 15th. A tiny number, right, raised to the third power. So this is tiny, right? But let's go ahead and do this. This is awesome. Okay, so alpha F1, and I've got 1.661 e minus 27 in the denominator, 4 divided by 3 times pi times 1.2 e to the minus 15th raised to the third power. This is 2.3 times 10 to the 17th. And that's kilograms per cubic meter, right? So this is equivalent to the density of a neutron star, right? The neutron stars have about this density, right? Because it's just basically neutrons. And the reason it's so dense and the reason that it doesn't vary is that the strong nuclear force is just so strong that as soon as these things bind together, it pulls them as close as quantum mechanics will allow it to pull. Okay, it's just so strong that yeah. It pulls them together, and it's not like it almost can pull them together, and that the density varies. It's that it just cranks on them, right? Okay. So the answer to this is that it doesn't vary, right? Show that the nuclear radius is that. So go ahead and use this formula, right? R naught, a to the 1/3, right? And I got that it's like 3.77 times 10 to the minus 15th, right? All right, and then this is formed when a nucleus of deuterium collides with that, right? So we've got a nuclear reaction here, right? Let's see, a nucleus of deuterium. Oh, interesting. Okay, so it must also then release must also release a proton, right? Okay, because notice the atomic number doesn't change yet. We're injecting a proton, right? The radius of a deuterium nucleus is 1.5 femtometers, right? State the maximum distance between the centers for the production which is likely to occur. Well, big and small, right? They got to touch. Okay, so what's the radius of the small one plus the radius of the big one, right? Radius 1 plus radius 2, right? You'll get something a little more than 5 femtometers, right? I got like 5.27 times 10 to the minus 15th, right? Determine in joules the minimum kinetic energy that the deuterium nucleus must have in order to produce that, right? So just use this potential energy one that we used for closest approach, right? KQ1, Q2 over R, right? Plug that in. One of them is 15E. Q1 is, you could say 1E, right? And Q2 might be the phosphorus nucleus, right, which would be 15E, right? Plug that in, and you'll get something times 10 to the roughly 7 times 10 to the minus 13th joules. Okay, that only electrostatic forces act. Yeah, okay. But the strong nuclear force doesn't interfere. All right, let's see. Okay, and then it says that phosphorus 15 undergoes 3215. So phosphorus 32, sorry, undergoes beta minus decay. Explain why the energy gained by the emitted beta particles in this decay are not the same for every beta particle. Okay, and the answer is that phosphorus, when it undergoes beta minus decay, right, we've got parent nucleus turns into daughter nucleus, plus in this case it's beta minus, right? So there's a beta minus, and then an anti-electron neutrino is also created, right? So the energy of the decay is shared between this, right? So if we take the mass of on the right side and the mass of the left side, we subtract, we multiply by 931.5, and we get the energy in millions of electron volts. That energy is randomly shared between the beta minus and the anti-electron neutrino. So therefore it's a continuous spectrum. The maximum energy for this corresponds to the energy of decay, but it's sort of like this graph that goes and there's this like cutoff there, right? That max of this is our energy this way, right? And this is our intensity this way. There's a cutoff right there, and that cutoff corresponds to the maximum energy of this decay. Okay, state what is meant by a decay constant. Well, that's your n equals n naught e to the minus lambda t. That's this, right? So what is it? It's the lambda is the per second probability of a particular nucleus decaying. So let's say you have a 1 in 5 chance every second of it decaying, then your lambda would be 0.2. Right? If you have a 1 in 100 chance of it decaying every second, it's 0.01, right? So the smaller that number is, the longer your half-life is, right? Okay, so there it is, right? All right, a fresh, pure sample, how would you do that, of phosphorus 32 in a fresh, the activity of the sample is 24 becquerels, so it's 24 counts per second, right? After 1 week, the activity has become 17 becquerels, right? Calculate in seconds to the -1 the decay constant of that, right? So we're going to do this, only remember that you can use this formula for anything that scales with the number of atoms, right? And since activity is lambda n, right? Okay, is it negative lambda n? I can't remember. Since it's, the rate at which we lose nuclei is lambda n, right? We can just throw the activity in there, right? So in other words, activity is the original activity, e to the minus lambda t. This works, right? You can also throw grams in there. You can do the original amount of grams. You can do the original activity, original number of atoms. Anything that scales proportionally to the number of atoms, you can just throw in here for n and n naught, right? So we're going to just do this. Our original activity was 24, right? The final was 17, right? And then 1 week later, notice that they want seconds to the -1, so time can't be in weeks, right? So that's going to be what, 7 days times 24 times 3600, right, to get seconds. A week is 7 days, each having 24 hours, and each hour having 3600 seconds, right? Okay. I got that it was on the order of 6 times 10 to the -7th probability per second. Okay. I think that's it for this guy.